So this is number 2 from the 2011 AP Calc AB, and this was actually also on the BC exam. So this was one of the problems that appeared both places. And it's a calculator problem, and it's pretty typical of a lot of calculator problems. They give you this table of values, and they're asking you to do these different things as you go through the 4 pieces of this particular problem. But basically we have a pot of tea that's cooling, and the temperature of the tea within the pot is measured at various values of T. So T is measured in minutes, and then the temperature of the tea is measured in degrees Celsius. And then what we're asked to do in part A is to try and estimate at what rate the temperature of the tea is changing when T is equal to 3.5 minutes. So a lot of the other times when we've had tables of values and we've been asked to estimate a rate of change or the value of a derivative, you would have to kind of realize that in this case, when they ask for a rate, that's going to indicate the derivative at this t value. So if we want to estimate this derivative at 3.5, we can't find it because we don't know what h of t is, but we can estimate it with the slope of a secant line. So 3.5 would be halfway in between these two t values. So if we found the slope of the secant line connecting these two ordered pairs, 2, 60, 5, 52, we're going to have a decent estimate. And so here's just the regular old slope formula: difference in y over difference in x, or difference in temperature over difference in time in this case, which is why it's measured in degrees Celsius per minute. And then if you simplify that, you end up with -8/3 degrees Celsius per minute. In part B, we are given this integral, and we're asked to try and explain what it means. Well, what you'd have to recognize is that the formula for average value of a function from the interval from a to b, on the interval from a to b, is going to be given by this expression. And what they've done is they've basically replaced the function within this with h of t, and the a and the b with 0 and 10. So this is really going to represent the average temperature of the t on the interval from 0 to 10, since this function within the integral represents the temperature of the t. So this will be the average temperature of the t as t ranges from 0 to 10. If you want to estimate the value of this with a trapezoidal sum, it can help if you start to plot the points. So I went ahead and I plotted the point 0, 66, 2, 60, 5, 52, and I kind of ran out of room here, but I could have plotted these last two ordered pairs as well. With the trapezoidal sum, we would just want to take the area of this trapezoid plus the area of this trapezoid. What I did was just use the regular old formula for the area of a trapezoid, the average height of the parallel sides, and then times the distance between them. So this was 66, this was 60, I took the average of those, and then I multiplied by the distance between those parallel sides, which would have been 2 units. And then for my next trapezoid, which you can also see up here, on the left edge we had a height of 60, on the right edge we had a height of 52. I took the average of those parallel sides, and then I'm multiplying by the distance between the parallel sides, which would be 3 units on the t-axis there. And then the next trapezoid would have these as the 2 parallel sides, so take the average of these, and then the distance between them would be 4, and then the last trapezoid, the parallel sides would be given by these 2 function values, so the average of these two, 43 and 44, and then the distance between those parallel sides would be 1 unit. Couldn't forget about my 1/10, just carefully got all this into a calculator and ended up with 52.95 degrees Celsius as the estimate for the average temperature of the tea. And if you think about it, that definitely does make sense. 52 is kind of the middle value here, and we ended up with an average that's slightly above that middle value. So it seems like this is quite reasonable. In part C, they've given us another integral, and they've asked for us to explain what it means and then compute it. And so what I did was I actually computed it first, and then I explained the meaning at the bottom here. To actually compute this integral, it's pretty simple, because using FTC part 1, first part of the fundamental theorem of calculus, we would need to take the antiderivative of this. Well, the antiderivative of a first derivative takes us back to the function. So the antiderivative of h prime is h of t. We would then need to evaluate h of t at these limits of integration and take a difference, so it's h of 10 minus h of 0, which, taking data from the table, h of 10 is 43, h of 0 is 66, so you get a value of -23 for that integral. Now what does it represent? Well, if you think about the units here, that can be a little helpful. So this is a rate of change of the temperature of the T, so it's measured in degrees Celsius per minute, and then this differential is measured in minutes. So we have degrees Celsius per minute times minutes. The minutes are going to cancel, and we're left with an answer that's just measured in degrees Celsius. So this number of degrees Celsius is going to actually represent the change in the temperature of the T from T equals 0 to T equals 10, and the fact that it's negative just indicates that the temperature went down from T equals 0 to T equals 10. Many times this year we've integrated a rate of change. This is the rate of change of the temperature of the T, and when we integrate that rate of change, we get how much change has actually occurred from this T value to this T value. So a drop of 23 degrees Celsius was the change in the temperature of the T from 0 to 10. And then the last part of this, we're told that biscuits are removed from the oven, initial temperature of 100 degrees right when they're removed. Temperature of the biscuits is going to be modeled by this function, but notice they didn't really give us the function b, they gave us its derivative, and we want to use the information we have here and this new model for the rate of change of the temperature of the biscuits to figure out how much cooler the biscuits are than the T at T equals 10, so after 10 minutes. So the temperature of the biscuits at T equals 10 is what we're going to have to find first. And to find that, we're going to take the initial temperature of the biscuits and we're going to add on how much the temperature of the biscuits has changed. So just like we said in the last part, this is the rate of change of the temperature of the biscuits. If you integrate that from 0 to 10, the value of this integral is going to indicate how much the temperature of the biscuits has changed from this T value to this T value. So if you did this on the calculator and then added it to 100, you'd get this value for the temperature of the biscuits after 10 minutes. And then to figure out how much cooler they are than the T after 10 minutes, well, you know the temperature of the T after 10 minutes is 43. Subtract that from 43, and there you have your difference.